All right, this video is for AP Calculus, and we're going to do the second half of a video on analytical evaluation of limits. Today we're going to talk about properties of limits and applications of properties of limits. So different textbooks define different properties. Some of them are universal, and then some include another property, which we'll discuss at the end, which has some caveats associated with it. But the ones that all textbooks describe these are true for all limits. If you have the limit as x approaches c of a constant, it's just simply equal to that constant. And most of these kinds of properties, you can it's sort of intuitive why this would be this way. So let's just take a look. If we had the limit as x approaches 8 of 5, then that means the graph of this function would just be y equals 5, which is a horizontal line. So it doesn't matter what x we're approaching, the output is simply equal to the 5. So that makes sense. Anytime you're taking the limit of a constant, there's no place to plug in the x, then the y is simply equal to the constant. That's an official property. Another property says the limit as x approaches c of the function x is equal to the c, and that makes sense because if you're saying the limit as x approaches 3 of x, that means the graph is y equals x, which means if you're approaching a 3 in the x, you're approaching a 3 in the y, and therefore that's equal to that. I wouldn't even consider that a property we have to know, but that is an official property. Okay, this next one is really important. We're going to take advantage of this quite a bit. The limit as x approaches c of f of x plus or minus a g is equal to separately the limits of the first and the second function. This is what allows us to do this. Let's say we have the limit as x approaches 2, and we have x squared plus x cubed. Okay? So what this is saying is that is equivalent to taking the limit as x approaches 2 of x squared and the limit as x approaches 2 of x cubed and simply recombining the results after taking the limit, which means if you have a function that's defined with pluses and minuses, right? Let's show a case with the minus. Let's say we have a limit as x approaches 3 of x minus 3x minus or plus x to the 5th. Each of these terms separated by pluses and minuses you can consider separate functions, and you can evaluate their limits separately and recombine them afterwards. So this could be the limit as x approaches 3 of the x, the limit as x approaches 3 of 3x, and the limit as x approaches 3 of x to the 5th. And then whatever number you get here, and whatever number you get here, and number you get here, you simply put those back into the equation with the minuses and pluses. Right, so that's really, really important. That will allow us to do a variety of different kinds of limits later on. Okay, next couple of properties. So this one says the same thing is true with things that are multiplied. If you have the limit as x approaches 2 of, say, the square root of x times e to the x, let's say something like that, that means that that's equivalent to the limit as x approaches 2 of the square root of x part and the limit as x approaches 2 of the e to the x part, okay? If you're coming to this class having taken AP Calculus AB last year, you might have remembered that when we did derivatives, we had a product rule. When things were multiplied, we had to do something more complicated. That is not true for limits. For limits, you can simply take the limit individually and remultiply the results. So sometimes you might not have a rule that works on this, right? But you can easily find the limits of the parts separately and then recombine them. All right, so those properties are in all the textbooks. This last one, some textbooks include, some don't, because it's tricky to implement this one. If you have a limit as x approaches c of what we call a composition of functions, so f of g of x, meaning that the g of x function is inside the f of x function, then technically, since the x is really right here and it's being applied to the g of x function, you can evaluate the limit as x approaches c of the g of x function first, and then plug the number into the f. Right? So I would say that it's tricky to implement this, right, though, because you have to be cognizant of the issues with the domains of the functions and what direction they're approaching. So this would suggest that if you had limit as x approaches 0 of the square root of 1 minus x squared, you could take the limit as x approaches 0 of the 1 over x squared part first, and then take the square root of this result. And that will likely work as long as you're careful about the domain. Let me show you some examples of this in use. Well, not that one, but just of these properties in general. So the first properties, the ones that are used all over the place, let's say we had to evaluate this limit. Limit as x approaches 2 of 2 times f of x plus 1 minus over 4 minus g of x. And these two functions were defined graphically. So we had a graph of this blue f of x function, this purple g of x function. Okay, I'm going to show you all of the properties in use here on this next screen. So first of all, there's a property that says that multiplying limits means you can multiply them separately. That applies for division as well. So we can say that this is equal to separately the limit taken on the numerator and the limit on the denominator. We can split it into a separate limit for each term, right? And then we're also, in this case, saying this is an example of a limit of 2 times the limit of f of x, but the limit of 2 is the constant. So that means that the limit of 2, which is 2, can just be multiplied by the limit. And then we can evaluate the limits here. Now, the limits of the constants, like this limit of 2, this limit of 1, and this limit of 4, just turn into the constants 2, 1, and 4. And we're just coming down to we only have to evaluate the limits of the functions. Right, so we are not required to write all this, actually. I'll show you what we'll write when we rework the problem, but I just wanted to show you that we're applying behind the scenes all these little properties. So if I evaluate the limit as x approaches 2 of f of x, we can do that over here. Limit as x approaches 2 of f of x is, okay, we have to go from the left and from the right. So the limit as x approaches 2 from the left is, well, this blue function. As we approach 2 from the left, this seems to be approaching 2 on the left for the y. As we approach from the right, this is also approaching 2, right, which means that limit is 2. We wouldn't necessarily have to write all this because this function is well behaved and there's a single rule. So I think we can just state that that's true and then insert that 2 in place of this limit in this expression. And then the same thing for g of x. In the vicinity of 2, the purple function is well behaved. So whether I'm approaching from the left or the right, the graph seems to indicate that this is approaching the number 3. So that'd be a 3. And then you could just leave it like that, or you can reevaluate this as 5 over 1 or 5. Okay, so this is all these properties being used. So how much would we really have to write on a test or for AP? I would say, I would probably do this much. I would say this is equal to the limit as x approaches 2 of just the number 2. Sorry. Back up here. This is equal to the expression 2 times the limit as x approaches 2 of f of x plus 1, because the limit as x approaches 2 of 1 is simply 1. And then this 4, technically it's the limit as x approaches 2 of 4, but it's just 4, minus the limit as x approaches 2 of g of x. Right, so I probably would write this, okay? And then I would just evaluate these in any way possible. So what would I plug in for the limit as x approaches 2 of f of x? I would go here and use a graphical technique. As we're approaching 2, the blue f of x function is approaching 2, obviously, from top and bottom, so I would simply write a 2 there, plus 1, 4, minus, and then the limit as x approaches 2 of g of x, as we're approaching x here, the purple function is approaching a 3. So this is what I would write. I would just write that. But behind the scenes, all these properties are being used. All right, so that one worked out pretty well. Now let's take a look at another example. This one's trickier. So let's say this is one of those compositional functions. So it's limit as x approaches 3 of f of g of x. So the g of x function's in there, right? And that means that that property says we can say this is f of the limit as x approaches 3 of g of x. Okay. So what we're going to do is we're going to first figure out what is this. Let me write that again. This is f times the limit as x approaches 3 of g of x. Let's work on that limit. What happens as x approaches 3 of g of x? Well, we should check from the left and the right, okay? Because if I look at the g of x function, which is defined here, as we approach 3, there is something unusual going on here. There's a change. So I'm going to say, okay, that's not well behaved in that region. I'm going to go ahead and look at the explicit limits on the left and the right. So the limit as x approaches 3 from the left of g of x. So as we approach g from the left, 3 from the left, this is approaching a 2, okay? And the limit as x approaches 3 from the right of g of x is also approaching a 2. So I can say that that is the number 2. However, notice something here. Because of the shape of this 2, we're approaching the 2 from the left, and we're also approaching this 2 from coming up from lower numbers. So it really would be better to say, although it's true the limit of x approaches 3 of g of x is 2, we should really say that the limit of x approaches 3 of g of x is approaching 2 from the left, right? We're coming up to 2 from lower numbers. Okay, so that is really approaching 2 from the left. Now, we're going to have to plug that into f of x, right? But we shouldn't just plug the 2 in, because the f of x function also has something weird going on at right near this value 2. It has a different value on the left and the right. So if I were to say, all right, I'm taking f of the limit as x approaches 3 of g of x, and this result is a 2, but being approached from lower values. That means that, that would specifically be this number, right? As we're approaching this x is approaching 2 from the left, we're actually approaching the value -1. So that means that we should declare that the limit as x approaches 3 of x approaches 3 of f of g of x is actually equal to -1. Right? So we have to be really careful about what direction. So if you have a function inside of a function, you have to also account for what direction the number is being approaching. Right? And that's particularly tough here because there are domain issues. Right? This function is defined, its domain, you can plug in any number from x is 0 to x is -infinity, and you get as a range -infinity to infinity out, right? That's not true. Actually, you only get, you only get the numbers -1 or 1 out as the range. Those are the only possible output values, right? Actually, -1 or 3, okay? And over here, the domain is any numbers from -infinity to infinity, but the range only goes from -infinity to 2. It never gives values above 2, so you can never approach this value from above 2. Right, so a lot of kind of tricky issues here. And I would just say that, maybe just summarize it this way. When in doubt, you should always check the sides. Now let's change the problem a little bit. Same limit as x approaches 3 of f of g of x. But what if I change the graph of this to not bend down like it was over here? In other words, not have a corner there. What if we just made it a smooth continuous line like that? What would happen? Now the range is different. This range goes all the way to infinity. And if we went through the same thing, the limit as x approaches 3 from the left, so as we approach 3 from the left, we're approaching 2 from the left over here. And then as we're approaching 3 from the right here, we're approaching 2 from the right here as well. And that means that we are actually approaching the number 2, right? But that means that if we are now going to say, okay, this g of x is approaching the number 2, but it's approaching the number 2 from both the left and the right, we don't really have a notation for that. But what that means is that maybe we should do the entire limit from the left and the right. So we come up with a notation for that as best we can. We've got the limit as x approaches 3 of f of g of x. So first, we'll do this. This is going to be the f of the limit as x approaches 3 from the left of g of x. I guess we could use this notation. So on the g function, if we approach 2, that's going to give me 2 as the output, but it's approaching from the left. So the result of this is that g of x is approaching 2 from the left. Okay? And then we're going to be plugging that function into f. This is not an official notation. But in the f function, if we're approaching 2 from the left, that means that this left limit would be equal to -1. And then if I wanted to try the limit on the right-hand side, that would be f of the limit as x approaches 3 from the right of g of x. And that means that g of x would be approaching, well, in this case, if we're approaching x is approaching 3 from the right, the g of x is approaching 2, but from the right. So that's approaching 2 from the right. And then if we're plugging that number that's approaching 2 from the right into f, that means we're on this side, which means we're approaching the number 3. So the left limit would be -1, the right limit would be 3. Therefore, we have to declare the limit as x approaches 3 of f of g of x without specifying a direction does not exist. Really tricky, right? So whenever you have a case where you have a function inside of a function, just know that you should back off and maybe try to do something like this. We don't really have official notation, but I think if you were to write this, we would be happy as calc teachers. I'm pretty sure the AP people would be happy. So you could just say, let's approach 3 from the left. Say the g of x approaches this number, but from a direction, and then evaluate what happens to the f function as that occurs. And separately from the right, and then evaluate if those two things are equal before you declare the limit exists. All right, so just a point of order here on these on the properties. All these ones are really straightforward. This one is tricky because of these issues. So when in doubt, just explicitly check the limits on the left and right side separately all the way through the problem, and then you'll be right answer. All right, so let's take a look at another problem. Why did we not have that issue with this problem, right? Well, the difference is that here we were evaluating the f of x limit completely separately from the g of x. We didn't have a composition of functions. So in that case, you should always be able to just directly plug in without having to consider the directions. Unless you see weirdness in the graph. Anytime you see corners or discontinuities, you should always just, when in doubt, check the limits separately on the left and right hand side. That will fix any problem. Okay. Couple more things to finish up this topic. There's a lot in this section. We're going to talk about an official theorem called the Squeeze Theorem. Sometimes this is called the Sandwich Theorem in older books. Same theorem. And it says this: sometimes it's difficult to evaluate a limit directly, but you can show that this function near the target x value is always in between the y values of two other functions. So you can say that your target function, you're trying to find the limit of f of x, maybe is always above h of x and always below g of x. So maybe there's this f of x function here. If you can somehow show that this complicated function is always greater in y than this simpler h function and always less in y than the g of x function, then if you can evaluate the limits of the h and g functions and they both evaluate to the same number, and that means that this more complicated function is also squeezed to that same number. This is the formal way it's written. If h of x is less than or equal to f of x is less than or equal to g of x for all x in an open interval containing the target x value c, except possibly at c itself, there could be a hole. And if you evaluate the limit of this function and the limit of this function at the target value and you get the same number L, then the limit of the inside function exists and is also equal to L. Right, so I'm going to show it one example of this. We don't use this very frequently, and I don't know that I've ever seen it on an AP exam, but good to know. Use the squeeze theorem to show that limit as x approaches 0 of x squared times cosine of 20 pi x is equal to 0. Illustrate by graphing the functions on the same screen. Okay, so this is a pretty complicated function. And if I plug in 0 here, that's a 0, right? That's a 0. But they're just asking us to use the squeeze theorem. So let's just go ahead and see how it would work. Okay. This more complicated function, if I'm trying to find the limit as x approaches 0 of x squared cosine of 20 pi x, would you agree that this cosine function, what does cosine do? As you put whatever x goes in here, we're just changing this angle, and it's going around this circle, this unit circle. Right, but the cosine is always staying between -1 and 1, right? Because the cosine is the coordinate on the unit circle. So that means that we either have the lowest value we would ever get would be -1 times this x squared, which is -x squared. And the highest value we would ever get would be +1 times x squared, which would be +x squared. And whenever cosine is anywhere in between -1 and 1, then that times x squared will be this. So that means that this function is in between these two functions, right? So what I can say is, erase that real quick. What we can say is, we can say since x squared cosine 20 pi x is less than or equal to x squared and greater than or equal, since this is true, our target function is always squeezed in between this function and this function, and we can take the limit as x approaches 0 of this -x squared function and evaluate it by plugging a 0 in and get 0. And we can take a limit as x approaches 0 of this x squared function and evaluate that by plugging in and get 0. Therefore, the limit as x approaches 0 of x squared times cosine of 20 pi x must also equal 0 by the squeeze theorem. Okay, so this is the squeeze theorem and how it would be invoked. Let's actually see that with a calculator so we can see what they're talking about. So if I graph this function, let me plug that in. We'll set limits too. So let's put in x squared times cosine of, let me make sure I'm in radian mode here. Yeah. Okay, so x squared times cosine of 20 pi x. Okay, and I'm going to zoom in here to kind of small numbers. Let's actually go. Yeah, that's fine, but let's just do the x's from -2 to 2, maybe. Okay. Okay, so here's that function. It's super crazy looking. Actually, I guess I need to zoom in more in the y. Let's do that. And the y will go from -2 to 2 as well. Okay, so here's this x squared cosine of 20 pi x, a very crazy function. But let me put on the graph -x squared and x squared. And so if I add to this graph -x squared and +x squared, there's the -x squared curve, and here's the +x squared curve. And you can see how this desired function, as complicated as it is always remaining in between these other two functions. So what we're showing here and here is that those two functions are both approaching y as 0, and therefore this more complicated function's limit as x approaches 0 is also 0. And that's it. That's really the idea behind the squeeze theorem. Whenever you invoke a theorem, you have to show its conditions are met. So in this case, the condition is that since the target function is always between the two lower and upper bounding functions, and the limits evaluate to the same number, the squeeze theorem will let you make this conclusion. All right, and then there's one last thing that I want to talk about here. This is, in my opinion, the least important of the topics, because later on we're going to have a better way to do this. But it is part of the course to talk about this here if we have not yet encountered derivatives. How can we evaluate a limit like this? Limit as x approaches 0 of tangent of 3x over tangent of 5x. We can't do any factoring here, although we could use some simple trig identities too. But we're going to take advantage of a couple of memorized predefined limits. Okay, one of them is anytime you have a function sine of any constant times x over that same constant times x, if you graph it, it will look like this. And that means that as x approaches 0 by graph, this is always equal to 1. And since 1 over 1 is 1, if you flip this upside down, cx over sine of cx, you'll get some other shape. but it will approach 1 right as x approaches 0. This rule is applicable only when x approaches 0 and only with this structure, sine of a constant x over constant x, or constant x over the sine of the same constant x. That's equal to 1. And then there's another limit that says if you graph the function cosine of constant x minus 1 over that same constant x, and you graph that as x approaches 0, that structure's limit is 0. And we can actually take advantage of that to help evaluate something like this if we didn't have a calculator. Here's how I would do it. This limit is equal to, we know that anytime I have a tangent of an angle, that's equal to the sine of that angle over the cosine of that angle. So I'm going to write that as a sine of that over 1 times 1 over cosine. Just split it up like that. So this limit is equal to the limit as x approaches 0 of tangent of 3x, which I'm going to write as sine of 3x over 1 times 1 over cosine of 3x. And then it's tangent of 5x. So that's sine over cosine, but the sine is on the bottom. So that's going to be times sine of 5x under 1 and cosine of 5x over 1. Okay, so we're going to plug this 0 in, evaluating each of these limits analytically. So the sine of 0 is 0, right? Unit circle, angle is 0. This is 1, 0. Sine of 0 is 0. Cosine of 0 is 1. So that means that this would evaluate to a 0 over 1, which is perfectly fine. We would be multiplying by a 1 over cosine of 0 is 1. That's perfectly fine. And this cosine would evaluate to a 1 over 1. That's perfectly fine. But if you try to plug in the 0 here, this sine of 0 is on the bottom of the fraction. So that one is not okay. And that's causing the issue there. All right, so how can we fix that? Well, we know that we were told that the limit as x approaches 0 of any constant of x over the sine of that same constant of x is actually equal to a 1, which means you don't have to plug in. You can just say by definition this is true. And the constant here is a 5, right? So what I'm going to do is I'm going to introduce a fraction. I'm just going to multiply by another term, and I'm going to get that 5x that I need. 5x over 5x. So I'm really just multiplying by 5x over 5x. But I'm going to choose to move this 5x over here. Okay, so that means I've got a 5x now over here. Now let me erase a couple things here. So that 5x is gone, and this is going to change, right? Because now, sorry, I'll make this readable. Okay, so now what do we have here? We've got 5x, this limit as x approaches 0 of 5x over sine of 5x, which since that structure is just the limit 1, it's been made into something that's okay. Right, that's removed that issue of dividing by 0. The problem is, now, we've got this 5x over here. So when we plug a 5x in over here, we get a 0. We're dividing by 0. Typically there's a 1 left there. And that means now we've just transferred the problem over here. We're still dividing by 0. So to fix that, we're going to multiply by another fraction. I'm going to use a different color here. Let's use this color. Okay. Although I don't need to, this sine of 3x is fine. I could pair it up with a 3x. So I'm going to multiply by 3x over 3x. Again, I'm going to move this 3x. Actually, let me do it up there. A 3x over 3x. Now I'm going to move this 3x to be over here. So I'm going to move it over here. And then that means that it goes away from here, and I'm left with just a 1 there. Okay, so I'm left with a 1 here. But that means I can recombine these into one fraction. So really this is 3x over 5x. So I could just now move this over here and get rid of this one altogether. Okay, but that means that now I could, now I could cancel it, factor and cancel out that final x. This would now change to a 1. This is that special structure whose limit is a 1. This, by plugging in, is 1 over 1. I don't have this anymore. This is the special function whose limit is a 1. This is by plugging in 1 over 1. And this is now the number 3/5. So we can conclude finally that the limit as x approaches 0 of tangent of 3x over tangent of 5x is equal to 3/5. All right, so we could evaluate this. This is the least used one, but it'll occur here and there in most practice homework sessions for this unit. So this is how you do that. You have to take the trig functions, expand them out into sines and cosines, and try to match up things of this form. If you can get limit as x approaches 0 of sine of a constant x over constant x, or constant x over sine of x, you can replace that whole limit with 1 without having to plug in. And if you can get cosine of constant x minus 1 over cosine of x, or c of x, constant of x, constant times x, the limit as x approaches 0 of that structure is 0. Okay, one more example. Let's say you want to evaluate this. We can't plug in because we have a 0 on the bottom. Right, but what we could do is take advantage of our trig identities and say this is equal to the limit as x approaches 0 of, I'm going to write that as a cosine x over 1. I've got this 1 over x. I'm going to write this tangent x as a sine of x over a cosine of x. And I'm going to split it out like that. And then I'm going to note that I can put those things together. Limit as x approaches 0 of cosine of x over 1. And you know what? I can put these together too. Over cosine of x, that's going to be cosine of x over cosine of x. And then these together are sine of x over x. This is simply the number 1. And that is sine x over x. So this limit evaluates to a 1, and this is that special limit, that the limit as x approaches 0 of sine of a constant x over the same constant x is also a 1. So therefore we can declare that the limit as x approaches 0 of cosine of x times tangent of x over x is actually equal to 1 by using this little trick. Okay, so just to summarize, here are the techniques for evaluating limits. I'm summarizing the last 3 videos here. So the first video we covered numerical and graphical. Numerical is the table of values approaching from each side. That will always work. Right? This is the fallback, but it's easiest to do if you have a calculator, right? Because a lot of times it involves using decimals. Graphical is the best if you have a graph in the problem, if you're provided with a graph. Then just use the graph, right? That's the best way to do it. This is our main method for when we have analytical approach to functions that are written out in expressions. Try plugging in the target value. If the result is undefined, then you can try various ways to simplify. You can try factoring or synthetic division. If you can get something that is algebraically equivalent, you can plug in the target value to that to find the value. If you have a radical, try rationalizing with the conjugate. And then you can also try these special trig limits, right? If none of those work, you can attempt the squeeze theorem. If you can't find a technique, but you could squeeze that function in between 2 other functions that you can easily evaluate to the same number, right? But ultimately, if none of those work, then you have to go back to numerical. That is the ultimate method that will always work. All right, so that is a lot of discussion, but really important topics about limits.